And let us go to the fourth presentation. Secure self-service, high-performance research computing in the cloud. The presentation will begin by Tara Madhyastha, principal research scientist at RONIN and professor at the faculty university. Yeah.
Hi. So, sure. Thank you. Yes, my name is Tara Madhyastha. I'm speaking to you from RONIN. Let's advance here. Okay. So I want to talk to you today about the platform called RONIN. It is a self-service research platform designed for researchers, like Dr. Carolyn Hogg, for example, here pictured with the Tasmanian devil. And she has goals of conserving endangered species. Other researchers want to cure diseases, understand climate change, develop new statistical algorithms. But increasingly, the common thread is that researchers find that to answer these questions, they need more computational power. But there are often limitations to the on-premise resources that they have access to. They may end up waiting for a long time in queues for HPC resources. They may not have the specialized hardware that they need, for example, GPUs. They often end up running out of storage space. And often, the use of HPC clusters doesn't really fit within their workflow. They're going from their desktop and they have to transfer data back, for example, for visualization and back again to run things again. And these things can be jarring, essentially, and interrupt the flow. In short, what researchers really want is unlimited access to the storage and the HPC resources that they need. But they want that to be as easy as using their own laptops. And they want everyone else pretty much to just get out of their way. The best way to find the kind of scalability and architectural flexibility that addresses these problems is on the cloud. But as we heard before, cloud computing is technically daunting, and fear of budget overruns can be real. And there's often a huge cloud learning curve to get to the point where you can use the cloud for research. I also point out that security is often a barrier because many researchers work in universities or labs where data are subject to specific compliance requirements. So there's this complex dynamic where researchers literally just want to get on with their work, but research IT needs to make sure that the data are properly secured. So this is what RONIN is designed for. It's a cloud orchestration platform that gives researchers enough flexibility to securely create any architecture that they need in minutes on the cloud, while at the same time allowing researchers to share and leverage software installations that have been optimized for specific use cases. Researchers do all sorts of things, a lot of custom work. It's very difficult to sort of templatize this, so it kind of has to be done collaboratively. Sometimes researchers themselves may optimize code for a particular platform, and sometimes it may be done with help from HPC or research computing specialists. And sometimes they may just try to run a script that doesn't work very efficiently, but they just need to get the answer. But because a picture is worth 1,000 words, it's easiest to show you what the user experience looks like. So I will start this, and it might be good to stop my video at this point so that we can see the full screen. But it creates abstractions that make it easier for researchers to use it. So rather than seeing, for example, a laundry list of services that may or may not be relevant, for example, here you see projects that are meaningful, collecting machines and storage and users together. Let's drill into this neuroimaging project, and because that is my area of research expertise. And you can see here that cost in the upper right is front and center. You can see what the budget for the project is, how much has been spent, how much is forecast, and how much is remaining. Fear of cost overruns is real, and research dollars are hard to come by. So it's really important that at every decision, researchers know how much things are going to cost. But that way, they have the flexibility to create the resources that they want. There's many types of things besides just compute that are important in a research computing environment, and that includes block storage, object storage, backups, versioning, and Ronin has support for all of these kinds of things. However, what I'm going to focus on today is how a researcher can create a self-service HPC cluster that's auto-scaling just for themselves. So that is one of the fundamental features that enables scalability for researchers and is a motivation for using the cloud. So creating an auto-scale cluster involves pushing a button basically and filling out a form that we'll see. Now, this is where self-service comes in. So it's possible in Ronin to package a cluster. Often the software that researchers are using is quite complicated. So there's this concept of an HPC project package. And here are, for example, two project packages that involve various collections of neuroimaging software and scripts and other things and data, all packaged. And these can be made available to all members of the project. In other words, my fellow researchers, or they can be promoted to the level of the organization and made available for other labs. This might make sense. For example, here you see that these two projects have been promoted to the use of the organization. And there's also a GROMACS package here that has optimized GROMACS for GPUs and a SPAC binary cache. So in this way, the HPC folks can work together with researchers to make packages available. You can also build a cluster from scratch. So you can select your base operating system, your scheduler. You do have this flexibility. And here's an example of the orchestration engine at work here. We can give the cluster a name that's friendly, and Ronin does the many, many, many steps involved in seeing whether this address is available and allocating it so that a researcher can use the name of the cluster rather than an IP address somewhere. Now, when it comes to selecting nodes for the cluster, I want to point out here that, for example, the head node, since it's on all the time, is often something very small. And so here it is a T3 small instance, which in AWS parlance is a burstable instance. So it's oversubscribed and you are limited in the amount of CPU that you can use. But we find that a lot of researchers actually like these. On the top here, you have more T instances in the quick select panel. They choose these because this means they get a dedicated cluster that's made of these tiny burstable instances, and it's really good for scripts that are not particularly well optimized. They have the ability to run in parallel, but it's very cost effective because they're not using the CPU very efficiently. But that said, many codes are not like that, and they will need access to all of the other types of resources that are available. And you can see here that you have access to FPGAs, memory optimized instances, GPUs, whatever you might need. If we drill down, for example, to compute optimized machines here, we can see that Ronin collects all of the information about the qualities of the machine, the amount of memory, storage, and in particular, of course, the cost, because at all times you need to sort of know what things are going to cost. Now, I've been focusing a lot on batch computing, high throughput computing, because that's characteristic of a lot of genomics applications and certainly my field, neuroimaging. But if you are running computational fluid dynamics simulations or weather modeling or any tightly coupled sort of MPI applications, you would look for those instances that have EFA enabled. That's Amazon's Elastic Fabric Adapter networking. So for low latency and the ability to scale to large numbers of nodes, those would be appropriate instances to use to build a more tightly coupled cluster. You can see here that there's the ability to change the amount of storage that you use for applications and for shared data. You can select a key. Key management is often a little bit tricky. And you can choose the minimum and maximum number of compute nodes. So we can actually set the minimum number of compute nodes to be 0 and use the head node like a workstation that can become a cluster as soon as you have work for it to do. And you can set the maximum number of machines to something large. So here, for example, now we have a cluster that has over 8,600 virtual CPUs for a single research project. So we have support for the Amazon spot market here. That is discounted discounted capacity. The drawback of that is that it can be reclaimed if that capacity is needed. So it's good for fault-tolerant applications or short-running jobs where the researcher can quickly restart and not lose a lot of work. So if you enable that, that can be quite a lot of savings on the cluster. We have support for, enabling the Intel HPC tools or disabling or enable hyper-threading for higher performance. And then what you see down below here is that you have a forecast of what this cluster is going to cost. So it goes from anything from the relentless use model where you're going and using the entire cluster for an entire week, to sort of a taper off model at the left there, where you may have jobs that stop and straddle down, or perhaps on the weekend, you're just using the cluster to start things and you look at them on Monday. And you can see that if you toggle on demand, that price will change. So we can launch the cluster. It takes about 8 minutes for the cluster to come up. So instead of waiting for that, I created a cluster already here, and we'll show you how you can access it. Accessing a cluster can be the biggest challenge for researchers as well. RONIN has an application called RONIN Link, which does secure port tunneling so that you can access a variety of different applications to get to your cluster. So we'll launch that. You can see here that the NeuralLab cluster is already connected in this card, so I don't need to recreate that. And if I look at the ways to connect to the machine, I have everything from a desktop, a terminal. The CPU monitor is Ganglia for monitoring of the cluster. If I have RStudio or Jupyter Notebook installed, I can use those. But getting a virtual desktop is a really nice feature to have for a cluster. I've already created this, so I'll just open this with DCV Link. That is the desktop virtualization platform that comes with EC2 instances. So we can open up a remote desktop onto the head node of this cluster. So this is incredibly useful for a lot of the workflows that researchers use where they have to visualize things, then recompute, resubmit jobs. You can see here what I have is a software called FreeView, which is a visualization package for the FreeSurfer cortical segmentation package. What this does, it segments the brain into gray matter, white matter, the cortex, and subcortical areas. And one of the things that researchers do is they check this because there can be errors in the segmentation. And as part of the protocol, often you have to go through every slice of the brain as shown here and notice whether there's problems, mark and annotate those. So in this workflow, a researcher could create this cluster, go through the results, and resubmit any jobs without having to move any data back and forth or disrupt in any way their flow. So let's go back now and close the circle. Imagine you're working on a cluster, you install software, you have packaged data, and now you want to save this for reproducibility. You're going to submit your paper, but they might come back asking for changes. Or perhaps you just want to make this cluster available to other people in your project. What you do is open up the tab here and package your cluster. So this will save the cluster, you can select what storage you're including with that, the root drive, or perhaps any applications or data with that. You give it a name, and then you can just save the cluster and use that. You can then, of course, as we showed earlier, promote that cluster to the organizational level with the help of the RONIN administrators if they feel that that's worthy of being shared. And that is how researchers can share these packages with each other across an institution or within an institution and across institutions. That concludes my demo, and I'd be happy to open it up for questions.
Thank you very much.
Hi.
Yeah, so I just there is one question. I will read it. Yeah, the costs seem high.
Mm-hmm.
I can see why an institution would prefer to invest in an on-premise HPC system, or is it really more cost-effective than an on-premise cluster?
The cost that I showed was for quite a large cluster. So, like I said, 8,600 virtual CPUs, and that was completely, undiscounted. So, one of the things to understand too is that AWS has various agreements and pricing that discount things that are not shown in the RONIN panels. So the expectation is that researchers should never be surprised by seeing something that is too low, and then they end up overpaying. So the cloud can absolutely be cost effective, especially with some of the smaller instances, and for the less and for the more bursty workloads.
Okay, thank you.
Mm-hmm.
Thank you. Yeah, thank you very much. And there is a second question regarding compatibility with or supporting. Yeah, is RONIN supporting other public cloud environments or resources? Yeah, AWS was presented by you, but the question is if we can talk about also other public clouds.
Currently, it is just supporting AWS.
Okay. Yeah, so thank you very much for the presentation. I do not see any other questions. Thank you very much.